In this demonstration, we're going to look at using the three conversion factors to work with the chemical formula of a compound, and I'm making up the compound C3H6Cl2. This is a chemical compound of a formula of substance we call a halogenated hydrocarbon. We have seen in our discussion that there are three conversion ratios that we can derive from an equation like this. One, of course, is the molar mass. In other words, 1 mole of C3H6Cl2 is going to have a total weight of 3 carbons, that's 36, plus 6 hydrogens, that's another 6, plus 2 chlorines, 35.5 each, so that's about 71, and that comes to a molar mass of about 113 grams of C3H6Cl2. Notice I'm doing this as a 3 sig fig calculation, which we often do in many calculations here. If it hadn't been specified and you had used 4 or 5 sig figs, measured that, added up this molar mass out to say the nearest hundredth of a gram per mole, that would be okay too. But notice, in other words, this ratio can be written as 113 grams of C3H6Cl2 over 1 mole of C3H6Cl2, and that's equivalent to writing the other conversion, 1 mole C3H6Cl2 over 113 grams C3H6Cl2. As with all ratios, which way you write the ratio doesn't matter. You'll write it in a way that is useful to you. The other conversion ratio here, and there are a number of them, I'm only going to write down 1 or 2 of them, refer to the subscripts. In other words, I can read from this equation there are 6 moles of H atoms for every 1 mole of C3H6Cl2. I could also write something to the effect that there are 2 moles of Cl atoms, for example, for every 3 moles of C atoms. Each of those can be written one way or the other, upside down, and you can come up with some other ratios here that would be useful. The third ratio that is going to be used occasionally, and the one that we use the least frequently, is Avogadro's number. The fact that there are 6.02 times 10 to the 23rd atoms or molecules, I'll write this as atoms, equals 1 mole of whatever that is we're speaking of. This can also refer to molecules or for ions. It's the same thing. That's Avogadro's number. And so I can write that one as, for example, 1 mole of, for example, carbon is 6.02 times 10 to the 23 atoms of carbon. I could also write, for example, that there are 6.02 times 10 to the 23 molecules of C3H6Cl2 for every 1 mole of C3H6Cl2. As always, these ratios can be written one way or the other, and as I said, with Avogadro's number, it can refer to atoms, such as carbon, or it can refer to molecules, in this example, C3H6Cl2. If I had a problem that asked me, for example, how many moles of chlorine in, say, 5.7 moles of C3H6Cl2, here's an example where I would simply take my given 5.7 mole C3H6Cl2 and write a ratio that I have, and in this case it would be a mole-mole ratio. It would look like one of these up here, to convert moles of the molecule into the atoms of the chlorine. And again, I can see it's 2 mole of Cl for every 1 mole of C3H6Cl2, and the answer here arithmetically would be twice 5.7, which would be 11.4 moles of Cl. And again, notice nobody's asking in this question how many atoms, they're asking how many moles. If, on the other hand, I had asked something to the effect of how many atoms of Cl in 5.7 moles of C3H6Cl2, I would be using two conversion ratios. The first would tell me the moles of chlorine, and I'm going to rewrite that just to illustrate the point of using tandem conversion ratios. If I start out with my given 5.7 moles C3H6Cl2, I would, of course, as I had before, said there are 2 moles of Cl for every 1 mole of C3H6Cl2. Then I would simply continue and write that there are 6.02 times 10 to the 23 atoms of Cl for every 1 mole of Cl. Notice the moles of Cl cross-cancel here, and the moles of the C3H6Cl2 cancel there. And running these numbers through the calculator, I would type in 5.7, again, times 2, and then just immediately times 6.02 E23, and the answer comes out here as on the order of, this should come out to on the order of, I'm going to run that through my own calculator. I think I made a mistake here. 5.7 times 2 times 6.02 E23, and that's coming out here, yes, to 6.86. I'm taking, actually, I should only show 2 figs here based on the 5.7, so let's just write that as 6.9 times 10 to the 24 atoms of chlorine. Notice when I was doing this with my calculator the first time, I did not hit the decimal point right there. And my answer came out 10 to the 25, and that's why I stumbled and thought about that for a minute. I'm estimating an answer here. 2 times 5 is roughly 10, times 6 is coming out to basically 6 times 10 to the 24. So when my calculator first read for me 25, I stopped and thought about that. I just missed the decimal here. So in any case, this is the correct answer, and it's also very useful to often estimate your answers. One more example of this, using this idea of these 3 conversion factors. Maybe I had given you, for example, a given value of 5.95 grams of, let's say, carbon, and the question was, how many grams of chlorine am I supposed to combine with that number of grams of carbon to form this particular compound, the C3H6Cl2? These are very common kinds of problems we will see in other contexts later, and I want to emphasize we're not using Avogadro's number here. Most problems in chemistry do not use Avogadro's number. I've used an example here to stress how it could be used, but the idea is Avogadro's number is only used when somebody either gives you the number of atoms or molecules, or they want to know the number of atoms or molecules. Otherwise, you don't have to use it. And here's a good example. I'm giving you grams, and I want to know grams of another substance. But so there's no reason to bring in Avogadro's number. I'm going to always start with my given, 5.95 grams of carbon. And the first thing I want to do is ask how many moles of that. Why? Because I know I have a ratio here of 3 moles of carbon to 2 moles of chlorine that is in my formula. So, but that's only mole relationships. That's not a gram relationship. So I write 1 mole of carbon is 12.0 grams of carbon I take from the periodic chart. Now I do know moles of carbon. And I want to make sure to write moles, and I want to write carbon also, because it's important here to keep one substance straight from another. We'll see many examples of this as we go through the class. So my next ratio is the fact there are 2 moles of chlorine for 3 moles of carbon. That's the recipe for this particular substance, C2H6Cl2. Now that I have moles of chlorine, notice the question here was grams of chlorine. So I'm going to write for myself, there are 35.5 grams of Cl for 1 mole of Cl. Remember, these numbers, of course, I'm getting off the periodic chart. Notice this ratio in between the two, the mole-mole ratio, is found in the formula. It's a subscript ratio. The other 2 ratios are molar mass ratios, analogous to the one I have back over here. And that's these are the 2 common ratios that are used in many of these calculations. Now, as far as the arithmetic is concerned here, I'm going to bring out my calculator again and type in my 5.95. This time be careful to hit that decimal. My own habit is to multiply everything on top first, so I'll write times 2 and then times 35.5. Then I'm going to go divide 12, and then again simply divide 3 and hit the equal mark. That's the first time I've hit the equal mark, and out pops the answer 1.17E1, so I'd probably just write that. I'm going to write that as a 3 sig fig number. Remember, this is exact, whereas I took 3 sig figs for the periodic table, from the periodic table, because I was given 3 sig figs to start with. So I'll simply write that as 11.7 grams of chlorine. That just tells me how many grams of chlorine I need to combine with 5.95 grams of carbon to get this particular compound. So I've shown you here the common ways in which we use these ratios, and you're going to find the most common ratios you use are the molar masses and the conversion ratios. And we'll see many examples of that as we go through the course.